So, okay, let's start. Baza, can you hear me?
Yes, sir. Assalamu alaikum.
Wa Islam. Okay, so this is W18 and it's question paper 2-2. Okay, that's the one that we're going to try and do today. So starting with the first one, TK, we're going to start with the first question, uh, which is about atomic structure. It says okay, the model of the nuclear atom was first proposed by Ernest Rutherford. He developed this model on the basis of results. Uh, so he's giving you that complete the table with the information for two of the particles in an atom of gold. So it's AU and it's 197. So it's I mean the relative mass is going to be 1 for a neutron, and the relative charge is going to be 0, and the location within an atom for an electron is going to be shells. And you're being asked the total number in an atom of gold. You can have a look at gold. Just one second. Let's open the keep the data booklet with us as well. So let's just have a look at the data booklet. Does it even know what gold is?
It's a transition method.
Benny, but what's the oh they actually gave you the I mean it's given over here. AU is the atomic mass is 197, nuclear number is 197, and the proton number is probably 79. We can have a look if this is open. TK, this is open now. We can. So gold is somewhere around over here. So it is 79. So that's gold. So you can just subtract the two, and you'll get the it's going to be 197 minus 79, and that's going to give you your the number of neutrons. TK, you can find it on your own. State the type of bonding in gold. That's going to be that's it's obviously a metal. It's metallic bonding. Then it says what is meant with the term isotopes. That's easy as well. It's basically uh, atoms of the same element. And what do they have? They have the same, having the same proton numbers. But they have different number of neutrons or different nucleon number. So the nucleons are different. Never write atomic mass over here. Atomic mass is something else. Atomic mass, relative atomic mass, is the average mass of an atom. When you talk about an isotope, make sure uh, I had previously in some lectures I described to you that nucleon number and atomic mass is slightly different. When you talk about the nucleon number, you're just talking about the number of neutrons and the number of protons put together. But when you talk about atomic mass, it's the average mass of an atom, and that includes the uh, masses of all the isotopes. So it's usually in decimals. It's approximately the same value, but usually in decimals. And mass is not mass is something that could be more and more accurate. Like if you talk about the relative mass, it's not exactly one because mass is something you measure. Quantity is something that you count. So when you're counting neutrons, it's always one or two. It can't be 1.1. So when you're talking about nuclear numbers, that's the number of neutrons and protons. That's always a whole number. That's always going to be. It's never going to be written in decimals. You either have 14 nucleons of like chlorine has 35 nucleons or 37 nucleons, but when you measure the mass, the relative mass, it depends on the accuracy of your instrument. It's close to one. What this means is that the relative mass is approximately one. That's close to one. It could be 0.999 or it could be 1.01. So it's usually in decimals. So when you talk about isotopes, it's the quantity of the neutrons that's different. So you have to talk about the number of neutrons or the number of nucleons. Don't write relative atomic mass or the atomic mass over here. So next is a different sample of gold contains more than one isotope. Suggest why this different sample of gold has the same chemical properties as. Why do they have the same chemical properties? They have the same electronic. They have the same electronic configuration. That's why they have the same. That's why they have the same property. Now, next question is this one. So next one is that there's an alloy of copper and gold. A sample of this thing is analyzed, whatever the name is. The mass spectrum of the sample is shown. So this is the relative, the masses of all the isotopes. There's a mass at 63, and the percentage abundance is 56.36. There's a mass appearing at 65, and the percentage abundance is 25.14%. And there's something that has a mass of 197. Now you're being asked calculate the percentage of gold X in the sample. So these two, the first thing is you're getting different atoms. You're getting two of these atoms and one of these atoms. Now this one, as we just discussed, this one is definitely gold. Gold is so gold. They've already mentioned it contains gold. So this one is gold. What are these other two samples? These must be copper. These must be isotopes of copper. So you would need a calculator for this as well. Let me take out my calculator. Now collectively, the sample was analyzed. So this is 56.36%, one of the isotopes of copper. The other one, 25.14%. So what is the percentage of gold? So together they should all be equal to 100%. So I'm going to take 100. I'm going to subtract 56.36 from it, and I'm going to subtract 25.14 from it, and I get 18.5%. So that's 100 minus 56.36 and minus 25.14, and I'm getting 18.5%. Okay, make sure somebody should try this on your calculator as well. See if I'm
Sir,
not
I'm
making
getting 18.56.
56.36, 25.14. No, it can't be 18.56. Can you try this again? Can you get 14 and
Getting
36? That's
18.5.
it should be exactly 18.5. Okay.
Yeah, 18.5.
So now calculate the relative atomic mass of the copper present in the sample. Give your answers to two decimal places. Now remember, he's asking you to calculate the relative atomic mass, which is the average mass of all the. So only this part. So you have to, I mean, get rid of the gold. Okay. He's not talking about gold. He's talking about measuring the relative atomic mass of copper. So how do you calculate the average? The average or the AR, the relative atomic mass, is calculated by multiplying the percentage of the isotope of copper, multiplying it by 63, plus the percentage of and the fractional percentage of the other copper, which is 65. That's how you calculate average. The fractional percentage would be over 100. So you sum up, you multiply the percentage by the atomic mass, and that's how you're going to calculate the average of the isotopes. Now 63 is 63. What percentage is 63? It's 56.36%. So so out of this sample, 56.36% is actually copper. Now there's one problem actually. Now this percentage over here, the one that I'm talking about over here, and this percentage as well. This percentage was calculated because it included gold as well. Like it wasn't out of 100%. Like 100% was this thing, the entire thing. Okay, so 56.36% includes gold. So you have to get rid of gold. Gold is 18.5%. So if I remove gold, because I don't want anything to do with gold. So out of 100, if I subtract 18.5, I get 81.5%. So this percentage is actually from 81.5. I mean, this is 81.5% of the thing. So I'm actually getting rid of I'm actually getting rid of gold over here. Okay. So this is 81.5%. So I need to actually calculate the percentage as well, because copper over here, this 63 copper is 56.36%, of 81.5% because I've removed the 18.5% gold that was also present. Do you get my point, Ethan? Is this point clear? Bazga, is this clear?
Yeah.
Mirahir?
Clear.
Yes.
ठीक है, तो the whole tricky part of the question was people would start taking 56.36%. It's not 56.36%. You would have to calculate the percentage again after removing the gold. ठीक है, you don't want anything to do with gold. So this fractional percentage 63 is how much? It's 56.36. ठीक है, it's 56.36 of 81.5%. Of 81.5%. And the other one, copper 65, that is 25.14% of 81.5%. So what is it? 25.14 of 81.5%. Now we can figure out the average relative atomic mass of copper. So that is going to be, can anyone try and calculate? It's 56.36 divided by 81.5. And then you multiply it by 63. And then you add the other one, which is 25.14 divided by 81.5, and you multiply that by 65. So I'm getting 63. I'm getting 63.616. So how many significant figures should I use? What I mean, he's using 4 significant figures. He must have no. He actually told you specifically to give your answer to 2 decimal places. So that's going to be 63.62. Is everyone getting this the same value?
Yes, I am.
Yes.
Okay, so it's 63.62%. Just be very careful with this thing. I mean, they're going to tell you. Otherwise, if they hadn't told you about this, you would use the rule, which is that you're going to use the least significant figures that are in the question. For example, over here, it's 56.36 or 25.14. So give your answer to 4 significant figures. The next one is the table gives some data of elements in the third period, and it's about the third period. So the first 3 are metallic. I mean, this one, magnesium is a metal, so that's metallic. This one is aluminum, is obviously a metal. Silicon is a macromolecular or a giant covalent structure. So it's a giant covalent. I think they're probably just asking for covalent or metallic, but we can write the whole thing. The formula of the oxide, sodium is +1, O is -2, so it's Na2O, MgO. Aluminum oxide, Al is +3, O is -2, so that's Al2, O3. And SiO2 is the giant covalent structure. And the formula of the chlorides, it's going to be AlCl3. This is SiCl4. Phosphorus has 2 chlorides. One is PCl3, and it could also have PCl5. Anyways, moving to the next part, complete the dot and cross diagram to show the bonding in a molecule of sulfur chloride. So chlorine makes only one bond. Here's this other chlorine that also makes one bond. Sulfur is in group 6, so it had 6 electrons. 2 are bonded now. These should be in crosses. So that's your sulfur. Next one is that complete and fully label the reaction pathway diagram for the reaction between S2Cl2 and Cl2 reaction pathway. So you had this reaction over here, right at the top. You had this reaction, and it was an exothermic reaction. The value was -40.6. So that means that your reactants would be higher than your products. It's an exothermic reaction, which means that the delta H would be pointing downwards. Remember, delta H starts from your reactants and goes to your products. The products in this case are, what are your products in this reaction? It's 2SCl2. And you had to label it. We've labeled delta H. We have to label activation energy as well, which is going to be delta E. It's going to start and go to the top. So these are the two things that need to be labeled over here. Now, on the axis, sketch the trend in melting points of the elements sodium to sulfur, and uh, you have to explain the melting points. Now, some of you probably did this in class. It's going to be just a second. Can you all hear me?
Yes.
Yes.
Acha.
Yes.
Acha, now Na is around 97. Uh, the melting points increase to magnesium, then aluminium, then silicon has a very high melting point. So it's going to look something like this, and then it drops all the way from phosphorus, and then slightly rises at sulfur. So that's how. And even after this, the sketch would look like this. There's going to be Cl2, and then there's going to be argon. So the melting point would further drop actually. Okay, so it's going to look something like this. So what's the reason? And we have to explain the sketch. The first thing is I'm going to check the marking scheme as well. What 3 points is he looking for specifically? We're going to talk about silicon first. Why does it have a such a large melting point? The reason for that is that it's a giant covalent structure. Okay, it's exactly like diamond. Silicon is that it would be tetrahedral. It would be bonded to 4 silicon atoms, and each silicon atom would then be further bonded to 4 other silicon atoms, and the structure would just continue, okay, like a diamond structure. So the giant covalent structures. So large amounts of energy are needed to break lots of covalent bonds. Actually, just 3 marks, so you just have to write just 1 point. Energy needed to break uh, a large number of covalent bonds. So, anyways, what about the first three? The first three are metallic. Okay, so Na, Mg, and Al are they are metallic or have metallic bonding. Okay, so they have metallic bonding, and Na has the weakest metallic bond, while the other one, aluminium, has the strongest. Okay, now I don't think there's enough space available to actually explain that further. But why does Na have what is metallic bonding? Metallic bonding is when you have a bunch of positive ions. Metals, they like to lose electrons. So metallic bonding is that you have lots and lots of positive ions because all the metals have they like to lose electrons. They're electropositive. They lose electrons easily, and the electrons are roaming somewhere in the middle. So why is Na the weakest? The Na is weakest because the charge on Na is +1, and it loses just 1 electron. So what is metallic bonding? Metallic bonding is the mutual attraction of the electrons and the positive ions. The delocalized, free-moving, mobile electrons are attracting the positive ions. So the positive ion is not really very, it doesn't have a very large positive charge. And there are not a lot of electrons in sodium. But when you reach aluminium, aluminium tends to lose three electrons, and therefore it has a plus three charge. So the positive charge is larger, the charge density on the positive ion is larger, and there are lots of delocalized electrons. So if you go towards aluminium, there would be a lot more delocalized electrons, and the positive charge on the ion is going to be greater as well, which is why aluminium uh, has stronger metallic bonds. Okay, is this Mohammed? Is this clear? Ethan, is this clear? Abba, is this clear?
Yeah.
Yes.
As a part three, what about these three? What's wrong with these three? They basically, basically, he was asking for the last two. Phosphorus and sulfur are simple covalent molecules. They basically have weak intermolecular forces. That should sum this up. Those should be your 3 points. You can explain this further. The trends in why phosphorus, sulfur, chlorine, and argon about the variation in the melting points of these substances. Uh, they all have van der Waals forces because they don't have dipoles because it's the same. Like phosphorus, it's just phosphorus, so there is no electronegativity difference, which means that there would be no dipoles. Sulfur is S8, chlorine is Cl2, and argon is a monatomic gas. Uh, so why is sulfur out of the four? Why is sulfur the highest? Because it has more van der Waals forces. And why does it have more van der Waals forces? Because it's the biggest molecule. Followed by phosphorus, then chlorine and argon. Also, I mean, there are no dipoles, nothing. It also has. Uh, it's going to have the least van der Waals forces. It's the smallest in relative size. So all of them are simple molecules, and they have weak intermolecular. One molecule attracting the other molecule very weakly with intermolecular forces, and the intermolecular forces are going to be van der Waals forces. TK, is this clear? Ibrahim, is this clear?
Yes, sir.
Yes.
I said the other one is SO2 can need write an equation of phosphorus with water. It's P4O10, and you react it with H2O, and it's going to form H3PO4. Phosphoric acid is going to be produced, and you can balance this. There should be four phosphoric acids. That's 12. That's six H2Os. So the oxygen looks balanced. Yes, it is balanced. So P4O10 is going to mix with water to form phosphoric acid. We can even go through the whole reactions of oxides with water. Just 1 second. Let me open. Let me open the notes for inorganic. Just 1 second. Probably this one. Yeah, actually not this one. These are just a second. We have a notes. TK, I did. I said these ones. They're here. I said these ones. So the reaction of oxides with water. These are all the reactions that you have to remember about period three. Like sodium oxide over here. It reacts with water to form NaOH. MgO also. MgO is not very soluble, so it's going to form a weak alkali. It's going to form magnesium hydroxide. Aluminium oxide is non-porous and unreactive to water. SiO2 is sand. It's not going to have any reaction with water. Remember P4O10, it's going to react with water to form H3PO4. And there's P4O6 as well. That's going to react with water, and it's going to form H3PO3, which is phosphorus acid. Same with SO3 and SO2. SO3 would react with water to form sulfuric acid, and SO2 would react with water to form sulfurous acid. As I said, this one, SO2 can be released into the atmosphere when fossil fuels containing sulfur are burned. State one environmental consequence of the release of SO2 in the atmosphere. So what happens? And he's specifically, I don't think he's asking for any explanation. What's the environmental consequence? Uh, Maybe I think they've given you enough line. You should add that SO2 reacts with NO2 in the atmosphere and ends up forming SO3. And NO in the process gets oxidized back. It acts as a catalyst and as an oxidizing agent. SO3 then mixes with rainwater to form H2SO4, which is your acid rain. And you can talk about one consequence of environmental consequence that soil. And remember, you have to be very focused on the environmental consequences. Uh, so soil and water bodies, they become acidic. Now, next one. Again, it's about period three. The elements in the period three show a general increase in their first. It's probably about ionization energies from left to right. Identify two pairs of successive elements in the third period that do not agree with this statement. For each pair, explain why the change in ionization energies does not agree with this statement. So he's talking about across the period. What happens when you move across the period, and what happens to the ionization energy? So the graph looks like this. So there's going to be increase. The general trend is increase. And it's going to look like this. There's going to be a dip at aluminium and there's going to be a dip at sulfur. Why does that happen? The first thing is, why is there a general increase across the period? And why do the ionization energies keep on increasing across the period? So the reason for that is that when you move across the period, uh, protons keep on increasing. So there's more nuclear charge. So that means electrons are attracted even strongly. The number of shells remain exactly the same. So the shielding effect is exactly the same. So the shielding is constant, uh, but distance slightly decreases. It decreases very. So if I can find an image of atomic radius across the period, so this one is a good representation. So as you move across the period, uh, the atomic radius keep on decreasing very slightly, not drastically. They have the same number of shells. Why do they decrease? Because the protons are increasing, so the shells are attracted even strongly. Like if you look at period two, there's let's look at period three. There's sodium, there's magnesium, then you have aluminium, and so on until you reach probably chlorine at the end and argon at the end. So there's a gradual decrease across the period because the protons are increasing. You have the same number of shells. Uh, so more protons, more attraction for electrons. So the size of the atom slightly gradually shrinks. So if you have more protons, the main factor is you have more protons. So there's a general increase in ionization energies, except for there's going to be a dip at aluminium at group 3 and a dip at sulfur. So what's the reason? Why is there going to be a dip at group? I mean, he's talking about the pair, and what period is he talking about? In the third period. So basically the same one. There's going to be a dip at aluminium. And why is there a dip? Because if you look at the electronic configuration of Mg, uh, it's 1s2, 2s2, and 2p6, and then there is 3s2. That's magnesium's electronic configuration. And if you look at the electronic configuration of aluminium, that's 13 electrons, so that's 1s2. Everything is exactly the same until the last shell, which is 3s2 and 3p1. So why is it easier to remove electrons from aluminium? Because you're moving an electron from aluminium, which is kind of further away. There's an extra subshell added in aluminium. So in aluminium, the electron is removed from a higher energy 3p subshell, which is further away, and also more. So which is further away and also more shielded. And you have to talk about comparison. Remember, you're given 5 lines, so you can add other things compared to. Always talk about the comparison compared to the 3s subshell in Mg. So that's what you're going to write for this. That magnesium, although aluminium has more protons, aluminium should be attracting its electrons more, but aluminium subshell is kind of slightly further away. And therefore it becomes kind of easier to remove electrons from a subshell which is slightly further away, very slightly, which is why you get this tip. Okay, is this clear? Minahil, is this clear? Abba, is this clear?
Yes.
I said then pair 2 was, what was pair 2? That's sulfur and phosphorus. That's, they're not agreeing with the trend that the trend should increase. So sulfur and phosphorus, that's so phosphorus and sulfur. What's wrong with them? Now, what's wrong with them is in phosphorus, if you write the electronic configuration, the end result would be that its last subshell would look like this. It's going to have 1 electron each. But when you move to sulfur, which has 1 extra proton, remember, it should have more attraction. But its outer electronic configuration would look like this. It's going to be 3p4, which means that it's going to be 2, 1, and 1. So why does it become easier to remove electrons from sulfur? Because the outer subshell has a paired orbital. Like there are 2 electrons in the same orbital, which means the 2 electrons are pushing each other away, and that makes it easier to remove electrons. Like in phosphorus, all electrons are singly filled. There is no repulsion. They're all existing in different orbitals. But in phosphorus's p subshell, there are 2 electrons in the same orbital, which is why there's going to be spin pair repulsion. So in phosphorus, electron is removed. Make sure you know how to express this. TK, make sure the best way is to just memorize these answers because these are going to be repeated a lot of times. So make sure you use the same terms. The same wording should be used. Not exactly the same, but the terms should be the same. So in phosphorus, electron is removed from a paired p subshell. That's actually incorrect. Not phosphorus, in sulfur. Okay, so in sulfur, electron is removed from a paired p subshell. Someone's mic is on, I think. So from a paired p subshell, and we can talk about the comparison as well. Compared to remember, always talk about the comparison compared to phosphorus, where electron is removed from an unpaired p subshell. So due to spin pair repulsion, it's easier to remove electrons in sulfur. So it's easier to remove electrons from sulfur because they're paired. They're 2 electrons in the same orbital. Okay? So is this clear, Mohammed? Is this clear? Rida, Heba, is this clear?
Yes.
As the next, and remember these two questions, they pretty much always come in papers. The dips at group 3 and group 6. ठीक है. The easier part is down the group, successive binary synergies, that's easy, but always remember, the problem with most students is they know the thing, but they can't really express. So it's better to actually memorize some of the words, some of the terms, some of the terminologies that are used when you're trying to answer this question. Uh, the next one is it's about enthalpy change. So you're given the data. You're saying the data to calculate the enthalpy change for the reaction. So this reaction, you have to calculate the enthalpy of this reaction. And what's given is you're given the enthalpy change of formation of the reactants, and you're given the enthalpy change of formation of the products. I think all of them are present. So CH3, AGF, AGI, all of them are given. So what is the formula for calculating the enthalpy change of a reaction if you know the enthalpies of formation of all the things involved in the reaction? So the formula is that the enthalpy of reaction would be the enthalpy change of formation of the products and minus the enthalpy change of formation of the reactants. So you sum up the products and you subtract the reactants. So what are your products? CH3F. So it's minus 692. So it's minus 692.9. Uh, that's CH3F. That's one of my products. The other one is 3AGF. AGF is minus 204.6, but it's going to be multiplied by 3. So these are my products now. 3AGI. The other one is subtract the reactants. Make sure you use the brackets properly because it's very important to get the signs right. So it's products minus the reactants. Now the reactants are CHI3, which is minus 182.1. Then you have 3 AGF. So what is AGF? That's minus 204.6, and that's going to be multiplied by 3. Remember, this is minus. Now get the signs correct. That's the first thing. Because a lot of people know how to do this. There are going to be calculation errors and lots of calculation errors in this. So if I open the brackets, this minus sign would actually become plus for these two. So this would be plus. Now try and calculate this, what the value is going to be. So it's going to be minus 692.
Sir,
Yes.
isn't one of the products AGI? You put it for AGF.
That's one mistake. Just be very careful. It's AGI, right? Wait a second. Which one should I drop? The product is AGI. AGI is 60. I mean, this should be. This is what was needed to be corrected, right?
Yes.
So be very careful with the calculation. You're going to make a lot of calculation, silly mistakes, basically. So it's minus 692.9. And everyone try and calculate this. A lot of people would get different values. Minus 61.8, and that's going to be multiplied with 3. And then you add. What do you add? You add 182.1. Even use calculators in your brackets. Plus 204.6 into 3. So I'm getting minus 82.4. I'm not sure. I'm using an online calculation.
I'm getting it too.
So probably that would be the right answer. So this would be, make sure you write the units. It's going to be kilojoules per. So it's going to be kilojoules per mole. That's going to be your answer to this part. Actually, they had given the unit. Now the graph shows the relationship between PV and B at a given temperature for CH3F3 and an ideal gas. Now this is an ideal gas. State 3 basic assumptions about the properties of ideal gas. 3 assumptions for gases. Number 1, negligible intermolecular forces. So that's number one. Number two is that the particles have large gaps between them, and the way that is expressed is that the volume of gas, the volume of particles is negligible. Negligible compared to volume occupied by the gas. And number three is that the collisions are elastic. So those are three assumptions. So explain why CH3F3 deviates from properties of an ideal gas at pressure greater than 300 atmospheres. So what's happening at this point at higher pressures? Why does it deviate? The reason it's going to deviate is like pressure is inversely proportional to volume. It's inversely proportional to volume. I'm going to explain it over here. That if you have a container and that container has a movable piston, so let's say there's this piston. Let me. Okay, so it has a movable piston and the gas particles in it. So let's say there are a bunch of gas particles in it. Now, if I increase pressure, volume should decrease. So pressure is inversely proportional to volume, right? So volume should decrease, and that makes sense. Keep on increasing pressure, the volume should decrease. Uh, but this relationship fails at high temperatures, high pressures, sorry. Why does it fail? Let's assume that the pressure has been taken to, you've taken it to a very high pressure. Let's say you're very close to infinite pressure. The volume should go to zero, right? Uh, this piston should move and should touch the base. If you increase the pressure a lot, the volume should go to zero. But the thing is that at a certain high pressure, gas becomes incompressible. When does it become incompressible? That if the gas particles, like you're increasing pressure and you've increased the pressure a lot and the piston is moving downwards, at a certain point, gases are only compressible as long as there are gaps between the particles. If you run out of those gaps, the gas would eventually become incompressible. Now the particles cannot be compressed anymore because you've removed all the gaps. Previously, there were gaps between gas particles. Now you've increased the pressure so much that that the gas becomes incompressible. So at very high pressure, and this happens at very high pressure only. So at very high pressure, what happens is you increase pressure. The volume should decrease according to the relationship, but the volume becomes, instead of decreasing, it actually becomes constant. Okay? No matter how much pressure you increase, the gas is not going to compress because there's no room left. All you have run out of all the spaces. Okay? Abba, is this clear? Hibanida, is this clear? Ethan, is this clear?
Yes.
So this relationship fails. It works most of the time, but at very high pressure, it's talking about 300 atmospheres and above. So at very high pressure, this relationship actually fails. It doesn't really work. Gas becomes completely incompressible. So what happens to your product? You were talking about the P into V graph, right? PV was plotted against. So PV is usually a constant, but it should be a constant. Why? Because if you increase pressure, the volume should decrease, right? So the product remains a constant, which is why for an ideal gas, he was talking about an ideal gas. If you look over here, for an ideal gas, this should be a straight line, uh, because this relationship for an ideal gas would be true. Ideal gas is a model of a gas. So keep increasing pressure, volume keeps decreasing, but the product remains a constant. But at high pressure, what happens? The volume stops decreasing, it becomes constant. You're continuously increasing pressure, but the volume is not decreasing. The gas is not compressing. So that means instead of actually becoming a constant, the P into V product would start to increase. Because you increase pressure, the volume remains constant, so your product actually starts to increase. Mohammed, is this clear? Ibrar, Bazga, clear?
Yes.
Yes, sir.
So coming back to the question, which is how do you write an explanation for that? What you're going to write is uh, so why does it deviate? So at high pressure, what happens is if you increase pressure, gas becomes incompressible. As particle volume no longer remains negligible. So gas becomes incompressible and volume stops decreasing. Okay, the ideal gas assumption was that there were no particles, like you could ignore the particles altogether. Because the particles were very far apart. So when you talked about a gas volume, it was basically empty spaces. So ideal gas assumed that you can simply ignore the particle volume. That's completely irrelevant. Uh, but at high pressures, that becomes relevant because why is the gas not decreasing? Why is the volume not decreasing? Because you're stuck with the particles now. So that's why the gas would become completely incompressible after a certain point. So that's going to be your explanation. That increasing pressure gas becomes incompressible as particle volume no longer remains and volume stops decreasing. Or you can also add that you run out of gaps. I mean, there are no longer any gaps between gas particles. Moving on, right? In equation, he's saying that trichloromethane reacts with O2 to produce this thing. So you have to write an equation. I think that should not be an issue. So it produces COCl2 and HCl gas is given off. All you have to do is you have to balance this equation. So there are three Cls. There are three Cls. I think it's already balanced. This should be half. That should do the trick.
Is it
Now,
writing it? Is it writing the product as COCl2 or CCl2O is the same thing?
this case, I don't think they would mind because I mean this thing is not in your. Nee, what are you saying? Okay, how should we write this?
The product, matlab you have written the product as COCl2. Can we write it
Mhm.
as CCl2O?
Same thing, I think. I mean, it should be the same thing. This thing is not in your course, okay?
Yeah.
So we're just giving the molecular formula. Well, he didn't actually ask about the structural formula.
Right. So matlab it doesn't matter if we write it this or that way.
हाँ जैसे मतलब ग्लूकोज है ना तो C6H12O6 है ठीक है so it doesn't molecular formula is simply you just sum the elements up which atoms and what are the quantities of those atoms ठीक है
Yes.
I said now this one infrared spectroscopy uh, he's talking about carbonyl dichloride which is this one. I'm just going to briefly go over infrared spectroscopy, which is simply, I mean, there's nothing to it except for the fact that these bonds over here, uh, if there's infrared uh, radiations of frequencies, then these bonds they vibrate. Okay, they start to vibrate to and fro, not only side to side, but they also stretch and compress. Okay, so bonds are not like fixed things. Uh, like anything, it's I mean they vibrate and they move to and fro, and they're going to absorb. Every bond is different. It's like a swing. Okay, like these bonds they can swing around. So every bond is different. And I'm going to relate this to a normal swing. Like if you have a swing and there is someone sitting on the swing, right, and uh, he's moving to and fro, right? That's like vibrations happening, but at the macro scale. So there's a person swinging. Uh, Now the thing is that the swing operates or absorbs frequency at a very specific frequency. Uh, like like if there's someone pushing from this side, he has to operate at a very specific frequency. Like you have to wait. Like if the swing goes up and then comes back, that's when you push, right? That's when you transmit energy. So waves are a means of transmitting energy in a cyclic manner, right? So this person over here who's standing over here and pushing this person and making him swing, he has to operate at a very specific frequency. You can't just go and wildly start hitting this person and expect the swing to sort of move around, right? I mean, you can try and start hitting the swing at random intervals. It's not going to swing. It's not going to absorb energy. So the same is true for these bonds over here. These bonds are like, I mean, they're going to vibrate like a swing to and fro, but they're going to absorb frequency at, they're going to absorb energy at a very, very specific frequency. They're not going to absorb any frequency. So all these bonds are unique. So this, I mean, there are basically two types of bonds over here. There's a CCl bond and there's a C double bond O over here. So all of them are going to operate or absorb frequencies at very specific, absorb energies at very specific frequencies. Is this point clear, Mohammed? Ethan, is this clear? Rida, is this clear?
Yes.
So here's your spectrum. This wave number is simply 1 over lambda. Okay, 1 over lambda is basically proportional to frequency because you know that V is equal to lambda f. So 1 over lambda is proportional to frequency. So this axis is 1 over lambda. Uh, or you can think of this axis as frequencies. So there are two frequencies getting absorbed over here. There's a frequency getting absorbed over here, and there's a frequency that is getting absorbed over here. The dips are the absorptions. So the conversion of, he's saying the conversion of CHCl3 to carbonyl dichloride can be monitored by infrared spectroscopy. And this is the carbonyl dichloride infrared spectroscopy, this molecule over here. And you can see that there are two types of bonds. There's a CCl bond that would be swinging around, stretching, compressing, and there's a C double bond O in this molecule. So you just have to relate which of these absorptions is due to CCl and which one is due to C double bond O. Now, on the infrared spectrum of carbonyl dichloride, identify with an X the absorption that would not be present in the infrared spectroscopy of CHCl3. So you just have to identify now CHCl3. What are the bonds that are missing? Like carbonyl dichloride has a C double bond O bond. So that's the bond that's missing in CHCl3. That would not be present. So we need to identify which one is C double bond O. Is it this one or is it this one? So for that, you would open the data booklet, and if you have a look at the data booklet, there's a page given over here where infrared. So there's a page given over here where infrared spectrum is shown, and you can see over here this is C double bond O over here. He's talking about amides, ketones, aldehydes, esters, all these compounds. They have C double bond O. It has a strong absorption, but the absorption is around 1600 to 1750. That's going to be your wave number. That's where the absorption is going to happen. So around 1600. So it's this one. This one is your C double bond O absorption. So that's where the absorption would be happening. So we need to explain the answer that it's going to be C double bond O first thing, as it is not present in CHCl3. And what were the two things that he was asking that you identify with an X? So we've already done that. That's X. TK, you can get rid of that other one. TK, is this clear? Bhaskar, is this clear? So just remember, infrared spectroscopy is a very tiny thing. TK, it's a very tiny topic. What you just need to know, I'll just go over that once more. What you just need to know is that all these bonds in a molecule, they're not fixed. I mean, you're talking about shapes of molecules, but even the shapes are kind of flexible, like in the real world. Like if a chair has 4 legs, the legs of the chair can actually, I mean, you can sort of bend them around and twist them around. Uh, so they can, I mean, they're not very rigid. They can vibrate, and each bond has is going to operate or vibrate at a very specific frequency, not at any frequency that it likes. So they're going to be unique frequencies that would be absorbed by each one of the bonds, and you just look at the dips. Okay, so you had two types of bonds, CCl and C double bond O, and from the data booklet we were able to identify that this is C double bond O. Next one is suggest another difference between the infrared spectrum of CHCl3 and I mean the other difference is CH. Like this one has a carbon and hydrogen bond. So just open the data booklet and see where is the carbon and hydrogen bond. I mean, it's over here. So there's going to be an absorption at around the 2800, 3000 range. You can have alkenes, or carbon and hydrogen bonds could be in any place, in a lot of places. So somewhere around 2800 to 3000, they are going to be, they're going to be absorptions wave number. This is, I think the unit is centimeter minus one. Let me just check what the unit is. Per centimeter, yes. So that's going to be centimeter minus one. And this is the only thing that you're going to mention, okay? So is this clear?
Yes, sir.
So now the other part is draw the displayed formula of P. Let me just see if we have done this. If we haven't done this, we're going to do this right now. Okay, I'm going to explain this. Uh, so the first part is diagram shows the reaction sequence starting from ethanol. So you're starting from ethanol. He's saying draw the displayed formula of P. Displayed means you show all the bonds. Now this first reaction, a lot of you haven't done this reaction in class. I'm just going to go over this. This is a reaction of aldehyde and ketones. Maybe you have done this in school. So aldehydes and ketones. In class, this is the next topic that we are actually going to do. So I'm just going to go over this very, very quickly so we can do the complete question. So you have a carbonyl compound. And in carbonyl compounds, there's a reaction mechanism that you have to study, which is called nucleophilic. It's called nucleophilic addition. What happens in nucleophilic addition is, that if you have a ketone or an aldehyde, which means there's going to be a C-double bond O. This is a highly polar bond. It's going to have carbon would be partial positive and oxygen would be partial negative. If you add these two things, HCN, that's your reagent, and NaCN, which is your catalyst in this case. So that's your catalyst. So if you add this, the CN minus 1 is going to get attracted to the carbon which is positive. It's going to act as a nucleophile. It's going to act as a nucleophile. Nucleophiles are attracted to positive charge. And when it gets attracted to the carbon which is positive, because CN is negative, the electrons over here are going to get repelled. So the next thing is the molecule that would be formed, there's going to be an intermediate that would be formed where there's going to be R and then there's carbon, and at the bottom, the CN would come and get attached. Whereas the oxygen electrons are going to get repelled and they would be pushed upwards. So that's what's happening. CN is coming in, bonding with the carbon over here in the middle, and the double bond electrons are getting pushed upwards. The next thing is the HCN molecule comes along with its positive H, and it would attract, or it would get attracted to the negative oxygen. And because the negative oxygen is going to come close to it, the electrons over here are going to get repelled. So your molecule that would be produced would be that it's going to be RC. The O would grab the H. The CN is attached at the bottom. And you have, and this CN minus 1 is regenerated. It's acting as a catalyst. It's not only a nucleophile, but it's also acting as a catalyst. And this CN minus 1 actually comes from NaCN. That's the only thing that you need to know about this reaction. So it's about aldehydes and ketones. The reaction that happens. So I'll just go over this quickly. Whenever you have serial bond O, but only in an aldehyde or a ketone, Cn minus 1 comes along, attaches to the carbon atom. The double bond electrons over there, they get repelled. So you get an O minus 1 over here with its lone pairs, and they then attract the H positive. And when they approach the H positive, the electrons over here, they get repelled. So Cn minus 1 is reformed. So that's your first step to this reaction. This is nucleophilic addition, aldehyde and ketones. So we have to draw the displayed formula of this molecule. So I'm just going to do this over here. It's the molecule is CH3, and there is serial bond O, and there is H, right? So what's happening? CN is coming in over here. It's attaching to the carbon in the middle. The double bond goes away, and it changes into OH. Now this is, so is this clear? Mohammed, is this clear? Ibrahim, is this clear?
Yes.
So the first CN is from the NaCN.
Yeah, I mean that's and then all the CN ions are produced from HCN after that. Like now there's going to be a chain reaction. Like you have CN ions getting reproduced. So you just needed this as the starting point to start the reaction, because HCN doesn't ionize that much. Because HCN HCN usually exists. It's a weak acid. It usually exists in the form of HCN. It doesn't ionize or produce H plus 1 or CN minus 1 ions that readily. Okay, so this one. So now the question was that they were asking for a displayed formula. Now you have to show all the bonds. Okay, you have to be very careful what type of formula they're asking for. So it's going to be CH3C, and then this is going to be O and H, and this is C triple bond N. Okay, make sure you show all the bonds. So that is what they were looking for. And next is name the type of chemical reaction that occurs in reaction number 3. So what's happening in reaction number 3 is what's happening in reaction number 3. This is known as dehydration. Like what's happening over here is, like if you look at our reaction number 3, this is another reaction that you study for alcohols. The OH and the H go away and a double bond is reformed. So that's a dehydration reaction. You must have studied this in O levels as well. Or you can also call it an elimination reaction. Now write an equation to represent reaction 4, use O to represent the oxidizing agent. So again, this one is, I think we would probably not be able to, well, let's study this, while we are at it. Now, reaction number 4 is about alcohols. So I'm just going to teach you what happens over here. Just like aldehydes and ketones, let's quickly discuss oxidation of alcohols, which we haven't done in class so far. So what happens in oxidation of alcohols? Now, in oxidation of alcohols, there are 3 types of alcohols. They are primary alcohols. You must have some idea what primary alcohols are. Primary alcohols are that the alpha carbon that is attached to OH, it has 2 hydrogens around it and only 1 carbon chain. So that's a primary alcohol. Now, when you oxidize a primary alcohol, so when you oxidize a primary alcohol, you need an oxidizing agent, which is K2Cr2O7. Potassium dichromate 6, acidified, and reflux. You could also use KMNO4 for that. And the color change is orange to green. What happens to this carbon atom? Remember, all the change that's going to happen is going to happen to the alpha carbon, which is the one that's attached to the functional group. So what happens to this is that this changes into an aldehyde first. So there's R still there, and it changes into an aldehyde, and it then further gets oxidized to a carboxylic acid. So it gets oxidized to a carboxylic acid. So this carbon, all the change that's happening is happening to this carbon atom. So this is the reaction sequence of a primary alcohol and a primary alcohol getting oxidized. Uh, Reaction usually doesn't stop at aldehydes. So what you need to do is, because reflux, remember reflux was used, if I had explained to you, reflux, things cannot leave the container. There's a condenser at the top. So anything that evaporates would quickly fall back into the container. But instead, if you want to stop the reaction at an aldehyde, uh, to stop reaction here, at this point, what you do is don't use reflux. Instead, use aldehyde, like allow the reactants to escape. So instead, use distillation. Distillation is that you allow the reactants to escape and you collect them through a condenser somewhere else. So why do you need to do that? The reason you need to do that is that alcohols over here and carboxylic acid over here, they have hydrogen bonding and they have higher melting and boiling points. So this has high melting point and this also has relatively, it also has relatively high melting points. Both of them have high melting and boiling points as well. You can be asked about this as well. Why? Because they can form hydrogen bonds. This over here can also form. This over here can also form hydrogen bonds. Now, if you want to stop the reaction at an aldehyde, this has low boiling points because it can't form hydrogen bonds. I mean, there is no OH group. So if you stop the reflux, if you don't use reflux, the aldehyde would immediately evaporate from the container and it would escape. So instead of changing into a carboxylic acid, it might change into a carboxylic acid, but instead of changing into carboxylic acid, the aldehyde would quickly evaporate from the solution because it has low melting and boiling points. And you can collect them through a condenser somewhere else. So you can use distillation. Allow them to escape. Is this clear, Abba, Rida? Is this clear? Mirahil, clear? Ibrar, is
Yes.
this? So just remember that primary alcohols, they change into aldehydes and then they change into carboxylic acids. And similarly, you have secondary alcohols. Secondary alcohols are, okay, what are secondary alcohols? So the alpha carbon would be bonded to two carbon chains. So let's quickly do that. Secondary alcohols are easy. That is going to have two carbon chains. And there's going to be an OH and there's going to be an H. So if you oxidize same reagents, it's going to be K2Cr2O7 or KMNO4, and you can use reflux. So it's going to be RC, R, and a ketone would be formed, double bond O. Make sure you should be able to identify. Make sure you should be able to identify which one is a primary alcohol and which one is a secondary alcohol. So carbon that's bonded to two carbon chains, it changes into a ketone. So ketones are produced. And the tertiary alcohols, they don't get oxidized. They're resistant to oxidation. So no oxidation of tertiary alcohols. So no oxidation of tertiary alcohols. Uh, so this is all about alcohols and their oxidation. Primary alcohols and secondary alcohols getting oxidized. So if you go back to the paper, you can see over here there's this alcohol. Let me highlight this. This is your alpha carbon. This is the carbon that's undergoing all the change. So what type of alcohol is this? Is this a primary, secondary, or tertiary? See, there's only one H attached to it.
Secondary.
Okay, so there's a carbon chain attached over here, and there's a carbon chain attached on this side. So this carbon atom would change into a ketone. So the R groups, nothing happened to the R group. There's CH3 and there's a carboxylic acid. They're still there. You can see they are still where they were. The middle carbon over here changes into a ketone. This one over here, the OH, the one with OH, that changes into a ketone. So he was asking, write an equation to represent reaction 4 and use O. So you're going to write an equation to represent this. So it's going to be CH3, CHOH, and COH. So CH3, CH, the middle one had OH, and then there was a carboxylic acid attached. And he's saying the oxidizing agent was K2Cr2O7. Now he's not asking for the whole equation. He's asking us to represent the oxidizing agent as an O. What's being produced? The thing that's being produced is over here. It's CH3, CO, and COOH. So it's CH3, CO, and then there is COH. Plus, now to balance this, there's going to be a water molecule that's going to be produced in this. If you try to balance this, there would be more hydrogens on the left side. The hydrogens are getting removed. That is oxidation. So you can try and balance this. So I think if we can balance it over here. 2 hydrogens got removed. I mean, it was CNO. It became CNO with a double bond, and the hydrogens are gone. There was a hydrogen over here and an extra hydrogen over here. So 2 hydrogens got removed, so that's H2O. And they probably combined with the oxygen over here to form water. And state the reagents and conditions for reaction 4. That is what we just did. It's K2Cr2O7 acidified, and there's going to be reflux. Okay. So yeah, that's part 4. The rest we can try and plan another class probably tomorrow. Then, okay. Clear? Quick question. We'll continue. Probably I'll try and find a time, okay, and I'll schedule one tomorrow as well. Okay.
Thank you.
Okay. Take care. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.